Review of basic data structures: array, linked list, stack, queue. An array is a data structure used to store elements of the same type. Arrays have a fixed size, and their elements are stored in contiguous memory locations. Here, we demonstrate how to declare an array in Python and access its elements. In the code, R is an array containing 5 integers. Arrays are zero-indexed, meaning the first element is accessed with R0. The code prints the first and fourth elements of the array, outputting 1 and 4. The use of arrays allows efficient access to data by indexing, but the fixed size limits flexibility. Abstract data types, ADTs. Abstract data types, ADTs, are theoretical concepts in computer science that define the behavior of data structures independent of their implementation. They specify the operations that can be performed, the type of parameters these operations can accept, and the return type of these operations. ADTs serve as the blueprint for implementing data structures in any programming language, ensuring that the fundamental characteristics and behaviors of the data structure are preserved, regardless of the specifics of its implementation. In the given code snippet, we define a stack class, an example of an abstract data type, ADT, implemented in Python. The stack ADT defines 3 core operations: push, which adds an item to the top; pop, which removes and returns the item from the top; and isEmpty, which checks if the stack is empty. These operations correspond to the ADT's defined behaviors without stipulating how these behaviors are implemented. This abstraction allows stacks to be used flexibly in different scenarios while maintaining their basic characteristics. Big O notation and complexity analysis. Big O notation is used to describe the efficiency of an algorithm in terms of time complexity, and space complexity, as the input size grows. It gives the upper bound of the complexity, helping us understand the worst-case scenario. Here, we'll look at a simple code example and analyze its complexity. The provided code defines a function that sums all the elements in a list. The time complexity is O(n), where n is the number of elements in the input list. This is because the loop runs n times, and for each iteration, it performs a constant time operation of addition. Therefore, the time it takes to run this function scales linearly with the size of the input, which is characteristic of an O(n) complexity. There's no significant space being used apart from the input, and a single integer for total, so the space complexity is O(1), indicating constant space usage regardless of input size. Recursion basics. Recursion is a technique where a function calls itself to solve a problem. A base case is essential to prevent infinite loops. In this example, we'll illustrate recursion by implementing a function to calculate the factorial of a number. The factorial function checks if the input n is 0. If so, it returns 1, which is the factorial of 0 by definition. This serves as the base case, stopping further recursive calls. If n is not 0, the function calls itself with n-1, multiplying the result by n. This recursion continues until n equals 0. Through each step, the function multiplies the current n value by the result of factorial n-1, effectively calculating n. Introduction to trees, terminology, and representation. Trees are a type of data structure that simulates a hierarchical tree structure with a root value and subtrees of children with a parent node. They are used in many areas of computer science, including database indexing, file systems, and more. Understanding the terminology and representation of trees is fundamental for grasping more complex tree-based algorithms. The code snippet defines a basic tree structure in Python. A class tree node is created to represent each node in the tree. It consists of a value and a list of children. The createSampleTree function initializes a simple tree with a root node and 2 child nodes. This example serves as a basic representation of trees, demonstrating how nodes are interconnected through parent-child relationships. Binary trees. A binary tree is a hierarchical data structure in which each node has at most 2 children, referred to as the left child and the right child. It's a foundational concept for understanding more complex trees and algorithms. Here, we'll implement a simple binary tree and add functionality to insert elements into the tree. This code snippet demonstrates the implementation of a basic binary tree with insertion functionality. The node class initializes a tree node with val as its value, and left and right pointers as none. The insert function recursively finds the correct position for a new value in the tree based on its size, maintaining the property of binary search trees where left children are less than their parent node and right children are greater. An example usage shows the creation of a root node with a value of 10 and subsequent insertions of 5 and 15, which would be placed as the left and right children of the root, respectively. Binary search trees, BST. Binary search trees, BST, are a type of binary tree where each node has at most 2 children. In a BST, all the nodes in the left subtree of a node have smaller values, and all the nodes in the right subtree have larger values than the node's value. This property makes searching, insertion, and deletion operations efficient. Let's take a look at how to implement a BST and perform a basic insertion operation. The code snippet defines a basic structure of a binary search tree and a method to insert a new value. We have a tree node class representing each node in the tree, holding a value and references to the left and right children. The BST class has an insert method that takes a root node and a val to insert. If the root is none, a new tree node with val is returned, effectively creating a new node. If val is less than root's value, it's recursively inserted into the left subtree, otherwise into the right subtree. This maintains the BST's ordering property. Balanced trees, AVL, red-black trees. AVL tree is a self-balancing binary search tree where the difference between heights of left and right subtrees cannot be more than 1 for all nodes. This ensures O log n complexity for search, insert, and delete operations. The balance is maintained through rotations during insertions and deletions. This Python function represents a right rotation in an AVL tree, a pivotal operation for maintaining its balance. When a node becomes unbalanced, indicating a higher subtree on the left, a right rotation on the unbalanced node might be necessary. The function takes the unbalanced node y as input, rearranges the pointers between y, its left child x, and x's right subtree t2. After the rotation, it updates the heights of the changed subtrees to ensure correct balance factors, and returns the new root of the subtree, which is x. This operation helps in maintaining the AVL tree's balanced property. B trees and B plus trees. B trees are a type of balanced tree data structure that maintains sorted data in a way that allows for efficient insertion, deletion, and search operations. They are especially well suited for storage systems that read and write large blocks of data. A B tree of order M can have a maximum of M1 keys and M children per node. The code snippet defines a basic structure for B trees. It includes a B tree node class with properties keys to store node values and child to store references to child nodes, marking whether the node is a leaf. The B tree class initializes with the root node and the minimum degree t, shaping the tree's branching factor. This structure forms the foundation upon which insertion, deletion, and searching methods get built, allowing the tree to dynamically maintain balanced properties during data operations. Tree traversals, in order, pre-order, post-order, level order. Tree traversals allow us to visit nodes of a tree in a systematic way. There are several types of traversals, each with its own application. In-order traversal visits nodes in a left root right sequence, useful in binary search trees. Pre-order traversal visits nodes in a root left right sequence, useful for creating a copy of the tree. Post-order traversal visits nodes in a left-right root sequence, useful for deleting the tree. Level order traversal visits nodes level by level from top to bottom, useful for printing the tree. The provided code defines basic tree traversal algorithms for in-order, pre-order, post-order, and level order traversals. In in-order traversal, we recursively visit the left subtree, print the root, and then visit the right subtree. In pre-order traversal, we print the root before recursively visiting the left and right subtrees. In post-order traversal, we recursively visit the left and right subtrees before printing the root, which is helpful for safely deleting nodes. Lastly, level order traversal uses a queue to visit each level of the tree from top to bottom, ensuring that nodes are printed in the order they appear from left to right. Tree operations, insertion, deletion, searching. In tree structures, specifically binary search trees, BST, insertion is a key operation that maintains the property where each node contains a unique value, A value less than a parent node is placed on the left, and a value greater is placed on the right. Here, we'll illustrate inserting a new value into a BST. The insert function takes two parameters, the root of the tree and the key to insert. If the root is none, the new key forms a new node that becomes the root. If the root exists, the key is compared with the root's value. If less, it's directed to the left subtree, if greater, to the right. This process is recursive, descending through the tree until it finds the correct position for the new key, maintaining the BST properties. Heap, min heap, max heap. A heap is a special tree-based data structure adhering to the property that each parent node is less than or equal to, in a min heap, or greater than or equal to, in a max heap, its child nodes. Heaps are widely used in algorithms like heap sort and for implementing priority queues. Here let's focus on implementing a min heap. In the provided code, we define a class min heap with an initializer that establishes an empty list, symbolizing the heap. The insert function adds a new value at the end of the list and ensures the min heap property by calling the percolate up method. This method compares the newly added element with its parent. If the new element is smaller, they are swapped. This process continues recursively until the min heap property is satisfied throughout the heap. The function getMin simply returns the smallest element, which is always at the root, index 0 of the heap structure, without removing it. This implementation underlines the importance of maintaining the heap's properties for efficient access and manipulation of data. Introduction to graphs and terminology. A graph is a nonlinear data structure consisting of nodes, also called vertices, and edges that connect these nodes. Graphs are used to represent networks, such as social networks, transportation systems, and communication networks. In the provided code, we define a simple graph class. It initializes an adjacency list to represent edges between nodes in the graph. Each edge is a tuple comprising two nodes, a source, src, and a destination, dest. The graph is created by iterating over a list of these tuples, edges, and populating the adjacency list with destinations. The adjacency list is an efficient way to represent graphs and allows for an easy way to find all vertices that a particular vertex is directly connected to. Graph representation, adjacency matrix, adjacency list. Graphs can be represented in several ways, the most common of which are the adjacency matrix and adjacency list. The adjacency matrix uses a 2D array where each cell, j, represents the edge between vertex I and vertex j. An adjacency list, on the other hand, is an array of lists. The index of the array represents a vertex, and each element in its list represents the other vertices that form an edge with the vertex. This code snippet shows basic implementations of graph representation using both an adjacency matrix and an adjacency list. The graph class is initialized with the number of vertices, setting up a square matrix and a list of lists for each vertex. The addEdgeMatrix method updates the adjacency matrix to indicate a bidirectional, undirected edge between two vertices by setting the corresponding cells in the matrix to 1. Similarly, the addEdgeList method updates the adjacency list by appending the connected vertex to each vertex's list. This shows a fundamental way to represent and manipulate graphs in programming. Graph traversal algorithms, BFS, DFS. Graph traversal is a technique used to visit all the nodes in a graph. Two common approaches are breadth-first search, BFS, and depth-first search, DFS. BFS explores the graph level by level, starting from a given node, while DFS follows a path from the starting node to the last node, then backtracks and explores other paths. The code snippet provided demonstrates implementations of BFS and DFS in Python. For BFS, we maintain a queue to keep track of the nodes to be visited next. We pop nodes from the queue, mark them as visited, and add their unvisited neighbors to the queue. For DFS, we use recursion. Starting from the initial node, we mark it as visited and recursively visit its unvisited neighbors. Both functions return a set of all visited nodes, providing a way to see the order in which nodes are visited, or to check if a node is reachable from the start node. Shortest path algorithms, Dijkstra's, Bellman-Ford, Floyd-Warshall. Dijkstra's algorithm is a graph search algorithm that solves the shortest path problem for a graph with non-negative edge weights, producing a shortest path tree. This example demonstrates Dijkstra's algorithm using a priority queue to enhance performance. The Dijkstra function calculates the shortest paths from a start node to all other nodes in a graph. It initializes distances as infinity for all nodes except the start node, which is 0. A min priority queue, implemented with a heap for efficiency, stores nodes by their current shortest distance. The algorithm repeatedly selects the node with the smallest distance, explores its neighbors, and updates their distances if a shorter path is found. This process continues until the queue is empty, ensuring that each node's shortest distance is calculated. Minimum spanning tree algorithms, prims, Kruskal's. Minimum spanning tree, MST, algorithms are used to find the subset of edges in a connected, weighted graph that connects all vertices together without any cycles and with the minimum possible total edge weight. Two famous algorithms for finding the MST are prims and Kruskal's. Prim's algorithm starts with a single vertex and keeps adding the nearest vertex that's not in the spanning tree until all vertices are covered. It maintains a priority queue of edges to efficiently get the next minimum edge to add. Kruskal's algorithm starts with all vertices isolated and keeps adding the smallest edge that doesn't form a cycle, using a union-find data structure to keep track of cycles. Even though the approach of each algorithm differs, both aim to minimize the total weight of the spanning tree. Directed acyclic graphs, DAGs. A directed acyclic graph is a type of graph that does not contain any cycles. This means that it is impossible to start at any vertex v and follow a consistently directed path that eventually loops back to v again. DAGs are fundamental in representing structures with dependencies among their elements, such as task scheduling, data processing pipelines, and more. The provided code demonstrates a simple implementation of a topological sort algorithm, which is a common and crucial operation performed on directed acyclic graphs, DAGs. The goal of topological sorting is to linearly order the vertices of a DAG, such that for every directed edge uv from vertex u to vertex v, u comes before v in the ordering. The way we achieve this in the code is by using depth-first search, DFS. We mark each node as visited to avoid revisiting and push each node onto a stack after visiting all its neighbors. This way, the nodes are added to the stack in a post-order manner. Finally, reversing the stack gives us the topological order. Topological sorting is essential in scenarios where dependencies matter, such as scheduling tasks that depend on one another. Topological sort. Topological sort is an algorithm applied on directed acyclic graphs, DAG, to linearly order the vertices in such a way that for every directed edge uv, vertex u comes before v in the ordering. This is particularly useful in scheduling tasks, arranging projects, and deciding on the order of compilation tasks. We'll explore a common approach using depth-first search, DFS, to achieve the topological ordering. The code defines a depth-first search, DFS, function that marks vertices as visited and explores deeper for each unvisited vertex, pushing it onto a stack after all its descendants have been processed, ensuring a vertex is pushed only when all vertices leading from it have been visited. The topological sort function initializes variables for visited vertices and a stack to store the topological order. It iterates through each vertex and calls the DFS function if the vertex hasn't been visited, thereby filling the stack with a valid topological ordering. The stack is returned at the end, which represents the topologically sorted order of vertices. Network flow problems, Ford-Fulkerson. The Ford-Fulkerson method is a greedy algorithm that computes the maximum flow in a flow network. It repeatedly finds augmenting paths from the source to the sink and increases the flow along these paths until no more augmenting paths can be found. Here's a basic Python implementation showcasing this method on a graph, represented as a dictionary of dictionaries, where keys are the nodes and values are the capacities of edges. The code defines two functions, Ford-Fulkerson, which implements the Ford-Fulkerson algorithm, and BFS, breadth-first search, which is used to find augmenting paths. Ford-Fulkerson repeatedly calls BFS to find paths from the source to the sink while there is still capacity for flow. For each found path, it calculates the minimum capacity, bottleneck, and increases the flow along the path by this amount, updating capacities accordingly. The loop in BFS traverses the graph level by level, ensuring that the path found is an augmenting one with available capacity. This process is repeated until no augmenting paths are found, at which point the max flow variable contains the maximum flow value from source to sink. Hash tables, hash functions, collision resolution strategies. Hash tables are data structures that store key value pairs. They provide efficient lookup, insertion, and deletion operations because they use a hash function to map keys to indices in an array, allowing direct access to the value. This basic hash table class example demonstrates how to initialize a hash table and apply a simple modulo-based hash function. The hash function takes a key and returns an index based on the remainder of the key divided by the table size, which is a common method to help distribute entries across the table. Trie, prefix tree, operations and applications. A trie, also known as a prefix tree, is a tree-like data structure that proves efficient for storing strings where keys are usually characters. Each node in a trie represents a character of a string. The root represents an empty string, and paths from the root to a leaf or node with a non-null value represent keys. Common operations include insert, search, and starts with. The code defines two classes, trie-node and trie. Trie-node is designed to represent each node in the trie, with children as a dictionary mapping each character to its child node, and isEndOfWord, indicating whether the node marks the end of a word. The trie class initiates with a root trie-node. The insert operation iterates over characters in the word, creating a new trie-node if the character isn't already present in the current node's children. It marks the last node as the end of the word. The search operation traverses the trie based on the word's characters and returns true if the word is found, indicated by isEndOfWord. The starts with function is similar to search, but only checks if the prefix exists in any of the paths starting from the root, not requiring a full word match. Suffix tree and suffix array. A suffix tree for a text is a compressed trie for all the suffixes of the text. It's a powerful data structure for string processing and comes with various applications in string searching, data compression, and bioinformatics. Building a suffix tree directly is complex, but structures like Ukonen's algorithm help construct it in linear time. Due to the complexity of building a suffix tree from scratch without specific algorithm implementations like Ukonen's algorithm, a code snippet is not provided. However, it's important to understand that a suffix tree allows for efficient string operations, letting you query the presence of substrings, find patterns, and even solve problems like the longest common substring in linear time relative to the length of the text. Spatial data structures, quad tree, octree, KD tree. A quad tree is a tree data structure used to partition a two-dimensional space by recursively subdividing it into 4 quadrants or regions. It's particularly useful in spatial indexing, collision detection in games, and storing sparse data like geographical information. Each node represents a bounding box covering a part of the space and has either 4 children or no children, leaf node. The provided code defines the basic structure of a quad tree node class, which will be used to build a quad tree. Each node stores its position with x and y coordinates and dimensions with width and height. The children attribute is a list initialized with 4 none values, representing the potential quadrants, top left, top right, bottom left, bottom right, that this node can be divided into. This class forms the foundational element of the quad tree, where each node can recursively divide the space into smaller regions. Persistent data structures. Persistent data structures are those which preserve their previous versions upon modifications, allowing access to any past versions in an efficient manner. In contrast to mutable data structures that are modified in place, persistent structures are crucial for applications like version control systems, where history is important. A common way to achieve persistence is by using immutable nodes, leading to partially new structures, sharing parts of the old ones. Let's demonstrate with a simple example of a persistent linked list in Python. In the provided code, node class describes a node in a linked list with value, holding the node's value, and next, pointing to the next node. The insert function demonstrates how to persistently add an element to the beginning of the list. When insert is called, it returns a new node that becomes the new head of the list, with its next pointing to the previous head. This way, the original list, 1, is preserved and can be accessed separately from the new list 2, 1, demonstrating basic persistence where both versions of the list are accessible and intact. Database indexing structures, B-trees, B-plus trees in databases. B-trees and B-plus trees are essential data structures used in databases for efficient indexing. They help in quickly locating records without scanning the entire database. A B-tree keeps keys in sorted order and allows searches, sequential access, insertions, and deletions in logarithmic time. A B-plus tree, an extension of B-tree, stores all records at the leaf level and includes a linked list among the leaf nodes for efficient range queries. The code snippet provides a simplified implementation of a B-tree structure. B-tree node class represents a node in the B-tree, containing keys and child pointers. B-tree class maintains the tree, including the root node and the minimum degree t, dictating the node's capacity. Each node can contain a maximum of 2 T1 keys. The insert method outlines how new keys are added to the tree. If the root is full, the tree grows in height by creating a new root. This basic structure and operation emphasize the logarithmic performance for insertions in B-trees, ensuring efficient indexing in databases. Introduction to dynamic programming. Dynamic programming, DP, is a method for solving complex problems by breaking them down into simpler subproblems. It is applicable where the problem can be divided into stages, with a decision required at each stage that will lead to a sequence of decisions. In DP, we use a table to store the result of subproblems to avoid computing the same problem again. Let's demonstrate this with the classic Fibonacci series problem, where each number is the sum of the two preceding ones. In this code, we solve the Fibonacci series problem using dynamic programming. First, we initialize a list DP with the first two Fibonacci numbers and placeholders for subsequent values. Then, we iterate over a range starting from 2, since the first two Fibonacci numbers are already known, up to n, the position of the Fibonacci number we wish to find. Within the loop, we calculate each Fibonacci number as the sum of the two preceding numbers and store it in the DP list. This approach ensures that each subproblem is solved only once, reducing the time complexity significantly compared to the recursive solution. Memoization versus tabulation. Dynamic programming is a method for solving complex problems by breaking them down into simpler subproblems. It is applicable where the problem can be divided into overlapping subproblems, which can be solved independently. Two main techniques to implement dynamic programming are memoization and tabulation. Memoization is a top-down approach, where we start solving the problem by breaking it down. If we come across a subproblem that we have solved before, we simply return the cached result. Tabulation is a bottom-up approach, where we solve all subproblems first and use their solutions to solve bigger problems. In the code above, for memoization, Fibonacci memo function takes an integer n and returns the nth Fibonacci number using a dictionary memo to store the result of each Fibonacci calculation. If the result is already in the memo, it returns the result without recalculating. For tabulation, Fibonacci tab function takes an integer n and calculates the Fibonacci sequence using an iterative approach and stores the results in a list fib table from the bottom up, i.e., it calculates all previous Fibonacci numbers before calculating the nth number. Memoization saves the result of expensive function calls and returns the cached result when the same inputs occur again, while tabulation solves the problem by filling up a table and builds the solution up to the original problem. Longest common subsequence. The longest common subsequence, LCS problem, is a classic in computer science, used to find the longest subsequence common to all sequences in a set of sequences, often just two sequences. It differs from problems of finding common substrings. Unlike substrings, subsequences are not required to occupy consecutive positions within the original sequences. The LCS problem has applications in file comparison, bioinformatics, and more. We will tackle this problem using dynamic programming, which efficiently solves this by breaking it down into simpler subproblems. The code defines a function LCS that calculates the length of the longest common subsequence between two strings x and y. It initializes a 2D list L of size m+1 x n+1 with none, where m and n are the lengths of x and y, respectively. This list is used to store lengths of LCS at different points, ensuring dynamic programming's bottom-up approach. The algorithm fills L by comparing all characters of x and y using two nested loops. If characters match, it increments the value by 1 from the diagonal value, li1 j1 plus 1, else it takes the max from the left or top, max lphi1j, lij1. The function finally returns the bottom right value of the matrix, lmn, which is the length of the LCS. Knapsack problem. The knapsack problem is a classic optimization problem that comes from dynamic programming. Essentially, it involves a knapsack with a fixed capacity and a set of items, each with its own weight and value. The goal is to maximize the total value of the items you can carry in the knapsack without exceeding its weight capacity. We will demonstrate the 0-1 knapsack problem, where each item can either be taken entirely or left behind, using a dynamic programming approach to solve it efficiently. The provided code defines a function knapsack that takes 4 parameters: the weight capacity of the knapsack, W, a list of weights of the items, WT, a list of values of the items, val, and the number of items, N. We initialize a 2D array K, where KIW represents the maximum value that can be obtained with the first I items and with W weight capacity. For each item, we decide whether to include it in the knapsack or not. If including the item doesn't exceed the weight capacity and increases the value, we do so. Otherwise, we skip the item. This is done by comparing the current value val_i_1 plus ka_1w item included with ki_1w item excluded, and taking the maximum of the two. Finally, the function returns the maximum value that can be obtained with n items within the weight limit W. Coin change problem. The coin change problem is a classic example of dynamic programming where you're given a target amount and a list of coin denominations. The goal is to find out the minimum number of coins needed to make up that amount. If it's not possible to make up the amount with the given coins, return -1. It's a problem that demonstrates the utility of breaking down complex problems into smaller, manageable subproblems. The given code defines a function coinChange that solves the coin change problem using dynamic programming. We initialize a DP, dynamic programming array with infinity, to represent the minimum coins needed for each amount up to the target. D equals 0 indicates 0 coins are needed for amount 0. We iterate through each coin and update the DP array, maintaining the minimum coins needed for each amount. If the final amount has a non-infinity value, it means the problem has a solution, and we return the minimum coins needed. Otherwise, we return -1, indicating it's not possible to form the target amount with the given denominations. Edit distance. The edit distance, also known as the Levenshtein distance, is a measure of how dissimilar two strings are to one another by counting the minimum number of operations required to transform one string into the other. The operations are insertions, deletions, or substitutions of a single character. A dynamic programming approach can efficiently solve this problem by breaking it down into simpler subproblems. This code implements the edit distance algorithm using a 2D array, matrix, for dynamic programming. The matrix DP is of size m+1 x n+1, where m and n are the lengths of 1 and star2 respectively. Each cell, dpij, represents the edit distance between the first I characters of star1 and the first j characters of star2. The code initializes the edges of the matrix with their respective distances, as converting an empty string to a string of length n, or vice versa, requires n operations. It then iterates through the matrix, calculating the minimum operations required by considering the previous operations, insert, delete, substitute, until it fills the matrix. The value at dpmn gives the minimum edit distance between the two strings. Maximum subarray problem. The maximum subarray problem involves finding a subarray within an array of numbers which has the largest sum. This problem is a classic example of dynamic programming and is often solved using Cadaine's algorithm. The essence of Cadaine's algorithm is to scan the entire array and at each point figure out the maximum subarray ending at that position. This is possible by keeping track of a current maximum sum and comparing it to a running sum, which is reset anytime it becomes negative. The function maxSubArray takes an array, nums, as input. It initializes two variables, maxCurrent and maxGlobal, with the value of the first element. It then iterates through the array from the second element onwards. For each element, it computes maxCurrent as the maximum of the current element, and the sum of maxCurrent and the current element. This step essentially decides whether to start a new subarray at the current element, if the current element is greater, or to continue the existing subarray. If maxCurrent is greater than maxGlobal at any point, maxGlobal is updated to maxCurrent's value. In the end, maxGlobal holds the maximum sum of any subarray within the input array, which is returned. Divide and conquer. Divide and conquer is an algorithm design paradigm that breaks down a problem into smaller instances of the same problem, solves the smaller instances, and combines their solutions to solve the original problem. This technique is particularly useful for solving complex problems efficiently. The provided code demonstrates the divide and conquer technique through the implementation of merge sort. The algorithm first divides the input array into two halves, then recursively sorts each half. Finally, it merges the two sorted halves to produce the sorted array. The key processes are 1. Dividing the array into halves until the base case, single element arrays, is reached. 2. Recursively sorting the subarrays. 3. Merging sorted subarrays to achieve the final sorted array. This technique exemplifies how dividing the problem into manageable parts and conquering each part can solve complex problems more efficiently. Greedy algorithms. Greedy algorithms build up a solution piece by piece, always choosing the next piece that offers the most immediate benefit. Though not always yielding the global optimum, they are efficient for some problems. Let's explore a classic example, finding the minimum number of coins that make a given value. This code snippet defines a function, minCoins, that takes a list of coin denominations, coins, the total number of coin types, m, and a target value, v, as input. It initializes an empty list result to store the coins that make up the minimum number needed to reach v. The function then iterates through the coin denominations in reverse order to prioritize larger denominations. For each denomination, it subtracts the coin value from v as many times as possible and adds the coin to the result list. This greedy approach ensures we minimize the number of coins. The example usage demonstrates finding the minimum coins needed to make a value of 121, assuming we have typical currency denominations. Backtracking. Backtracking is a systematic way of trying out various sequences of decisions to reach a desired goal. The method is used to solve problems that can be broken down into smaller problems of the same form. When an approach to a solution fails, this strategy discards the current sequence of decisions and backtracks to try another sequence. It's akin to navigating a maze. If you hit a dead end, you retreat and try a different path. The provided code illustrates a backtracking algorithm to solve the n-queens problem, where n represents the size of the chessboard, nxn. The goal is to place n queens on the board such no two queens threaten each other. The recursion explores each row by attempting to place a queen in each column. It avoids placing a queen in any column, diagonal or anti-diagonal, already threatened by another queen. If a column, diagonal or anti-diagonal, is free, the function tentatively places a queen there, adds it to a set, and proceeds to the next row. If a dead end is reached, it backtracks by removing the queen and trying the next column. The process repeats until a solution is found or all possibilities are exhausted. The algorithm returns the number of possible solutions. Branch and bound. Branch and bound is a powerful algorithmic technique designed to solve optimization problems. By systematically exploring branches, it efficiently finds the optimal solution. This technique divides the problem into smaller parts, branches, and evaluates them using a bound function to eliminate non-optimal solutions, thus narrowing down the search space. Here, we use it to solve the 0-1 knapsack problem, which aims to maximize the value of items in a knapsack without exceeding its weight limit. In this branch and bound example, we solve the 0-1 knapsack problem. The function knapsack is defined to calculate the maximum value that can be achieved within a given weight limit, W. It takes the weight limit, W, list of item weights, WT, their respective values, val, and the total number of items, N, as inputs. The function uses recursion to explore the decision tree by considering two cases for each item, including the item in the knapsack or not. The maximization condition selects the branch with the higher value until all items are considered. This is a simplified demonstration of branch and bound, focusing on understanding how branching decisions lead to the optimal solution. Randomized algorithms. Randomized algorithms use a degree of randomness as part of their logic. They are especially helpful for problems where a deterministic approach may be too costly or difficult to implement. A simple example is the use of randomization in the quicksort algorithm to select a pivot. The performance of these algorithms can often be average case or expected case rather than worst case. In the provided code, we implement a simple version of the quicksort algorithm using randomization to select the pivot element. This approach can improve the average case time complexity compared to consistently selecting a bad pivot, e.g., always choosing the first or last element, especially in sorted or nearly sorted data. First, we check if the array is empty or has one element. If so, it's already sorted. We then select a random element as the pivot. The array is partitioned into elements less than and greater than the pivot. The algorithm is recursively applied to these partitions, concatenating their results with the pivot in between. This random pivot selection makes quicksort more resilient to worst-case scenarios, thus highlighting the power of randomization in algorithms. Amortized analysis. Amortized analysis is a technique used to analyze the average time complexity of operations in a sequence, guaranteeing the average performance of each operation in the worst case over a sequence of operations. It's different from average case analysis because it doesn't assume any probabilistic distribution of inputs. It's particularly useful for data structures with operations that have varied time complexities. We will examine the aggregate, accounting, and potential methods through a common example, implementing a dynamic array like Python's list or Java's ArrayList. In the code, we're looking at a simple implementation of dynamically resizing an array when appending an element once its capacity is reached. Initially, the operation might seem costly due to the need to double the array size and copy elements over to the new array. However, when analyzed with amortized analysis, we find that this operation has an amortized cost of 0.1. This is because, for each expensive resizing operation, there are several 0.1 append operations that don't require resizing, spreading the cost of resizing over numerous cheap operations. Thus, the average time per operation remains constant, demonstrating how amortized analysis provides a more nuanced understanding of algorithmic efficiency. Basic concepts of concurrency and parallelism. In computing, concurrency and parallelism are two fundamental concepts that enhance the performance of executing tasks. While they might seem similar, they address different aspects of multitasking. Concurrency involves multiple tasks making progress within the same time frame, but not necessarily simultaneously. Parallelism, on the other hand, refers to the simultaneous execution of multiple tasks. In the provided code, we demonstrate a simple example of concurrency in Python using threading. We define two tasks, each of which prints a message. We then create two threads, thread 1 and thread 2, each targeting one of the tasks. By starting the threads with thread1.start and thread2.start, we allow the tasks to run concurrently. This means task 1 is being executed and task 2 is being executed could be printed in any order, depending on how the threads are scheduled. The join method makes sure that the main thread waits for both threads to complete before proceeding. Locks, mutexes, and semaphores. Concurrency structures such as locks, mutexes, and semaphores are crucial in ensuring safe access to resources in multi-threaded applications. They help avoid race conditions by controlling the sequence in which threads access shared resources. Locks allow only one thread to access a resource at a time. Mutexes are similar but can be unlocked only by the thread that locked them. Semaphores manage access by a fixed number of threads. Each concept plays a pivotal role in maintaining data integrity and preventing deadlocks. The code demonstrates basic usage of mutexes, locks, and semaphores in Python with the threading module. The mutex object is a mutual exclusion lock, ensuring that only one thread can enter the critical section of the code at a time. With mutex.acquire, the critical section starts, and only the thread that acquired the lock can release it with mutex.release. On the other hand, the semaphore allows up to 2 threads to enter the critical section simultaneously, indicated by threading.semaphore2. Each thread must call sem.acquire to enter and sem.release to leave the critical section. This exemplifies controlling access to shared resources in a concurrent environment. Concurrent data structures, concurrent hash map, lock-free structures. A concurrent hash map allows multiple threads to read and write in a map without causing data inconsistencies. Java's concurrent hash map class is an example, designed for thread-safe operations without the need for explicit synchronization. Let's see how we can initialize and perform basic operations. The code snippet initializes a concurrent hash map, then adds a key value pair with put, reads the value with get, and finally removes the entry with remove. Concurrent hash map internally handles synchronization, so these operations are thread-safe, allowing concurrent reads and writes without external synchronization. This makes concurrent hash map highly efficient for concurrent applications. Actor model and its applications. The actor model is a conceptual model that deals with concurrent computation. It treats actors as the universal primitives of concurrent computation. In the actor model, an actor can perform the following actions: send a finite number of messages to other actors, create a finite number of new actors, and designate the behavior to be used for the next message it receives. It does not share state with other actors, making it a powerful tool for designing and reasoning about systems that must operate in concurrent or distributed environments. In the code snippet, we've defined a simple version of the actor model using Python classes. The actor class has an inbox for messages and can send and receive messages. To send a message, the sendMessage method appends a message to the recipient's inbox. To process an incoming message, the receiveMessage method pops the first message from its inbox and processes it. Although rudimentary, this demonstrates the key concept of the actor model. Actors communicate by message passing and manage their own state. This setup can be extended for more complex scenarios, including asynchronous message processing and distributed systems. Software Transactional Memory, STM. Software Transactional Memory, STM, is a concurrency control mechanism that simplifies the development of concurrent programs by allowing code to execute in transactions, which are sequences of operations that appear to execute atomically. If a transaction fails due to conflicting access to shared data, it is automatically rolled back and retried, offering a way to manage access to shared memory without explicit locking mechanisms. Below is an example code snippet showcasing a simple use of STM in Haskell, a language that has built-in support for STM. The code demonstrates a basic example of using software transactional memory, STM, in Haskell. Control.concurrent.stm is imported for STM operations, and control.concurrent for threading capabilities. The main function creates a shared transactional variable, shared counter, initialized to 0. It then forks 2 threads, each incrementing shared counter by 1, using modify TVR within an atomic transaction, atomically. After a brief delay to ensure both threads have completed their increments, the final value of shared counter is read atomically and printed. This showcases how STM can manage concurrent updates to shared data without explicit locks, providing an elegant solution for dealing with concurrency complexities. Parallel algorithms and data structures. Parallel algorithms and data structures are designed to leverage multi-core processors, allowing multiple operations to execute simultaneously, improving performance for computational tasks. We'll explore a simple example of a parallel algorithm that computes the sum of an array. This code snippet demonstrates a simple parallel algorithm to sum an array. It uses Python's multiprocessing.pool to divide the array into 2 halves, then recursively sums each half in parallel. Once both halves are calculated, their results are summed. This approach can dramatically reduce the time required for large arrays by utilizing multiple cores to perform calculations concurrently. However, it introduces overhead from process creation and communication that may not make it suitable for small arrays. Data structures in networking. Trie in IP routing. In computer networking, particularly in IP routing, a trie is a type of data structure that enables efficient information retrieval, commonly used for storing and searching IP routing tables. The trie structure is ideal for this application because it can match IP addresses to their corresponding network prefixes in an efficient manner. Here, we will explore how a basic trie can be implemented for IP routing. The provided Python code defines a basic implementation of a trie for IP routing. The trie node class represents a single node in the trie, with a dictionary children to hold child nodes, and a boolean is end of word to indicate if the node represents the end of an IP address. The IP route trie class manages the trie and includes insert and search methods. The insert method adds a new IP address to the trie. Each part of the IP address, assumedly a digit, navigates or creates a new path in the trie. The search method checks if an IP address exists in the trie by navigating through the trie using the parts of the IP address. This structure is efficient for matching IP addresses with their network prefixes, crucial for IP routing, as it allows for quick searches and insertions. Data structures in compression. Huffman tree. Huffman coding is a lossless data compression algorithm. The process involves creating a tree where each leaf is a character in the file to be compressed. Characters that occur more frequently are given shorter codes, and less frequent characters receive longer codes, enabling efficient compression. Here, we're implementing a basic Huffman tree for a given set of characters and their frequencies. The provided code sample constructs a Huffman tree for a set of characters and their respective frequencies. The node class represents each node in the tree, holding a character, its frequency, and pointers to left and right child nodes. The createTree function builds the tree using a priority queue, min-heap, to ensure nodes with lower frequencies are combined first, which is crucial for Huffman coding efficiency. Characters are initially stored as individual nodes in the priority queue. Two nodes with the smallest frequencies are combined into a new node, merging, and this process repeats until there's only one node left, representing the root of the Huffman tree. Data structures in databases, B-trees, tries. In databases, the efficiency of data retrieval and storage is paramount. Two crucial data structures facilitating these operations are B-trees and tries. B-trees are used for indexing and ensuring quick access to disk-stored data, while tries are utilized for efficient searching and storing of strings, such as a dictionary or autocomplete features. B-trees are balanced tree data structures that keep data sorted and allow searches, sequential access, insertions, and deletions in logarithmic time. They are widely used in databases and file systems to store information that does not fit entirely in memory, ensuring efficient access to disk-stored data. Each node in a B-tree contains a number of keys and pointers. The keys act as separators to divide its subrange of values into subranges, with each subrange corresponding to a child pointer. The B denotes the balancing of the tree, crucial for maintaining low height and thus reducing the disk accesses required for operations. Tries, on the other hand, are special types of trees used to store associative data structures. A trie is a rooted tree where each node represents a common prefix of some strings. Each node may contain a character, and paths from root to leaf in the trie represent words or sequences stored in the trie. This structure enables extremely fast retrieval of items by key, especially useful for autocomplete suggestions, spell checking, and IP routing. Unlike B-trees, tries are particularly efficient for handling cases where the keys are strings. Machine learning algorithms data structures, KD trees for nearest neighbor search. KD tree, a space partitioning data structure, is instrumental in organizing points in a k-dimensional space, widely used in nearest neighbor search. This example illustrates constructing a KD tree and using it for a nearest neighbor search. The focus is on the implementation for a two-dimensional space for simplicity, although the concept extends to higher dimensions. This code snippet defines a basic usage of KD trees for nearest neighbor search using Python's scipy.spatial.kdtree module. Initially, a list of sample points in a two-dimensional space is defined. These points serve as input to construct the KD tree. The KD tree object is then utilized to efficiently find the nearest neighbor of a given query point, 6, 3. The query method of the KD tree object performs the nearest neighbor search, returning the distance to the nearest neighbor and its index in the original list. Finally, the nearest neighbor along with the distance is printed. This demonstrates the effectiveness of KD trees in facilitating swift nearest neighbor queries, a pivotal operation in many machine learning algorithms. Blockchain and cryptography data structures, Merkle tree, blockchain. Blockchain and cryptography data structures, such as Merkle trees and the blockchain itself, are fundamental to the operation of cryptocurrencies like Bitcoin. A Merkle tree allows efficient and secure verification of content in large data structures, while the blockchain is a decentralized ledger of all transactions across a network. Here, we'll focus on implementing a simple version of these concepts. This code snippet demonstrates the foundation of a Merkle tree, a crucial part of blockchain technology. It includes two functions, hash pair, which hashes together two inputs, and Merkle root, which recursively combines and hashes pairs of elements, transactions, or other data points, until a single hash remains, known as the Merkle root. This process ensures data integrity across the blockchain. If even a single transaction is altered, it would result in a completely different Merkle root, thus signaling a tampering attempt. This mechanism allows for secure and efficient verification of large datasets in distributed systems.